So anyhow, thanks for having me. I'm essentially going to talk very informally about the work we did compiling cryptographic code to WebAssembly, the challenges that we encountered, and like just a few thoughts on what we hope to achieve. It's not a super, a high stakes presentation. It's informal. It's a small group of people. Interrupt me. I know that I talk a lot, so you should interrupt me and ask questions in the middle. It'll make the whole thing much more interesting. All right. So this work is part of a Project Everest, which you may or may not have heard of, but essentially it's a big joint initiative between several institutions that you can see at the top, INRIA, KReMLin, Microsoft Research. And so specifically, I'll focus on one sub part of Project Everest, which was our work compiling some of the crypto code from Project Everest to WebAssembly that was published a couple of years ago. Okay, so there's a lot of people involved with Project Everest, lots of people across the world, and we're generally a fun bunch. I'm sure you've seen some of these names seem familiar, or some of the people in this picture also seem familiar. We're all very friendly and very easygoing. So if there's ever such a thing again as conferences in person, I highly encourage you to come and say hi. So I'm going to start with a little bit of context and motivation around Project Everest, just to give you a sense of what this is and how we're basically relating to various other initiatives. So essentially, Project Everest started maybe 5 years ago, and the initial impetus, the initial momentum was that there's a big software stack, which is the HTTPS software stack, and it's wildly insecure. So HTTPS is quite critical. It's the most widely deployed security protocol. Nearly all of the internet traffic these days is over HTTPS, thanks to efforts like Let's Encrypt. And it's used not just for HTTPS, but there's also a lot of other protocols for email and voice over IP and VPNs that use such TLS implementations. So essentially, HTTPS is a big stack with various subparts. One of them is TLS, the Transport Layer Security Protocol, which is about doing a handshake and establishing a secure connection. And I'm not going to talk too much about TLS today. But my point is that it's a big software stack, and specifically, there's a bunch of cryptographic algorithms that are used all throughout the stack and that are used especially for TLS. And it's not going to shock anyone in the audience if I say that it's a very buggy software stack. The way that I present it, and the reason why I personally like this, is that there's every single kind of issue you can think of. It's like a wonderful cornucopia of issues and attacks. There's buffer overflows, there's wrong state machines, you get parsing issues, you get wrong crypto, you get side channels. It's a festival of errors. So, of course, when you're a researcher, you're like, ooh, sounds good. I'm going to look at this in detail. And, well, the problems are actually, when you look at, when you ask what the problem is, it's really a variety of things. It's that the security goals are not clearly stated. It's actually quite hard to come up with a crisp definition of what a secure protocol is. The APIs are poorly crafted. Just look at OpenSSL. The standards are sometimes outdated. And so the idea behind Project Everest was to try to verify large chunks of this software stack and to have finally some strong security result. That was the initial, impetus. And one goal was to make it usable and deployable. One of the requirements was that we wanted to see some of this code land in existing software ecosystems, and ideally in the process build trustworthy, usable tools. So here's a quick timeline of Project Everest, just to give you a sense. I need to make this smaller. Okay. So I would say that everything started in 2016 when we had a student start looking at cryptographic algorithms and verifying them in FStar and extracting those to a camel. So the workhorse of Project Everest is the FStar programming language. FStar supports a variety of targets for its extraction, that is compiling your verified program in FStar to an existing backend. And like after the initial attempt of generating all of that verified software in OCaml, we found out that it's too slow and that essentially people do not want to integrate OCaml into their web browser, no matter how wonderful the language is. And so I would say that in 2017, one key design choice was that we were going to generate C code. The architecture is as follows. You write your code, you verify it, you state the security properties in the F-star language, and then you extract that code to C code that can then be readily integrated into existing software ecosystems. And so we have had a variety of papers, both on the foundations and on the applications. And we slowly worked our way up the big software stack that I was showing on the previous slides. So we spent a couple of years working on verified cryptography, compiling to C. That's the HACL project for high assurance cryptographic library. We also have a way to generate x64 assembly, and that's the Veil project for cryptographic algorithms. We started looking at parsers, which is another big part of that software stack. Another project that brings the assembly and the C implementations together under a big unified modern API is EverQuic for Everest crypto library. We started moving further up the stack, looking at actual applications such as Signal, the QUIC record layer. And in the meanwhile, we continue to improve our techniques and refining our verified crypto library to have like parallel SIMD implementations. We have successfully managed to deploy a lot of the code in known and famous pieces of software. One of our greater successes has been with the NSS crypto library from Firefox, where last time I checked, we had nearly 25% of their crypto algorithms implementations were from us. We also have an excellent working relationship with Jason Donaldford, the author of the WireGuard VPN software, who's been like a big fan of our approach and has integrated Curve and has given us like tons of useful advice on how to generate C code that people want to use. There's a blockchain that seems quite popular these days called Tezos, and they also are using a large amount of crypto primitives from our code through their OCaml bindings. So now we have C library, and then we have OCaml bindings on top of it to make it easy for people to get fast crypto, but still call it from their favorite language. ARM embed has been using Curve 25519. We have some code in Windows. We have some code in an enterprise blockchain from Microsoft called CCF. And we also have like a large amount of code in something called Kaizala, which I understand is a popular enterprise messaging software, mostly in India. So this is basically the software stack that we're at. And what I'd like to do now is give you like a more close-up view of the language that we use, our compilation pipelines, and of course, how we repurposed some of that compilation code generation pipeline to WebAssembly. Are there any questions at this stage?
I had a quick question, or hope maybe it's not a quick question. You said that you originally had OCaml bindings, but then those were too, like the performance wasn't good. But you didn't give it like any insight as to why the performance wasn't good. So I was curious if you could give like a high level sense of what the paradigm change did for you.
Yeah, essentially crypto is a very like strange world where no performance hit is acceptable. It may or may not be justified in the grand scheme of things, but if you're slower than the like state-of-the-art, carefully tuned implementation that's written in a mix of C and assembly, then you lose a lot of credibility. The reason why it was slow in OCaml is simply because of the runtime representation of OCaml. OCaml uses tagged integers, so they have like 63-bit integers where you have the lowest bit that indicates whether this is an immediate value or a boxed value. And so all the algorithms were optimized for 64-bit exactly, with like carefully crafted leftover bits that would hold some carries or some extra data. And the fact that we didn't have that representation generated like a huge performance hit.
Okay, so essentially impedance mismatch of representation was the...
Yeah.
Great, thanks.
So it was 2016. The student, Jean-Karim, did his first version of OCaml, and it was great to understand like how to verify that code, but then he repurposed it to generate C code directly. And then he got the speed that he was hoping for, and then we got a lot more credibility. Yeah, and it's also that people don't want to integrate like anything written in OCaml into existing software, right? I mean, I'm sure like I could go to the Firefox folks and be like, look at OCaml, it's great. It has lambdas and it has modules and functors, and it comes from France, thumbs up. But I'm not sure that they want to integrate, something like that in the web browser. All right, so enough about general context. Let me just like zoom in a little bit. So we have a big pyramid now of verified software. Each part of that pyramid has properties of interest in addition to like the basic results of memory safety and functional correctness. And I'll get to those in a minute with more detail. The crypto, for instance, has properties of side channel resistance. The applications have confidentiality and integrity. And like some parsers may have properties regarding like non-malleability, for instance. And so there's a subset of this pyramid that compiles to WASM, and that's the signal protocol, the EverQuic crypto library that dispatches between the C implementations and the assembly implementations. And so the C implementations have also been recompiled to WASM. So that slide is just about like to set the ideas on what is being verified, right? Just to make sure we're being clear about it. Safety is a property such as no buffer overruns, no dangling pointers, no use after freeze. So that's basic memory safety. Functional correctness, we showed that the crypto code and the code that we generate in general behaves exactly as the specification, which is simple, readable, and auditable. We have results about secrecy, which is that we don't access secrets wildly. And we have, for the top of the pyramid, some results about cryptographic security, where we put some results in the computational model. We bound the probability that an attacker may break some security properties. So it's important to understand that there's limitations. There's assumptions such as the outer application that uses our code will not destroy the private key or will not do anything crazy with it. There's some assumptions, of course, such as a discrete logarithm in a finite field is hard, and that's like an assumption that we take for granted. We also work with like a very simple setting, right? Our models are not as precise as would be required to model Spectre, for instance. And the various steps of our compilation toolchain, which I'll get to in a minute, are not verified themselves. But there's also advantages. Everything is automated. We have like compositionality. We can extract some subbits of our pyramid and distribute them as standalone projects. And then we've managed to keep that big pyramid of verified code alive for the past 4 or 5 years. So before I tell you how we compile to WASM, I think a little bit of context on what exactly the toolchain we use would be helpful. So one constraint that I mentioned is that users want familiar technology. They don't want OCaml. They want something that can be integrated, reviewed, and understood. The quality of the code that we generate and that we like, produce as part of our verification toolchain needs to be very professional, and it needs to be very fast. So all of these are reasons why OCaml wasn't like a good target for our verification pipeline. Instead, we chose to generate C code, and that turned out to be a very fortuitous choice. So let me now get a little more concrete and show a little bit of code. I want to explain how we start from F star, our source verification language, and generate C code on the other end. So F star is a dependently typed language that essentially resembles OCaml. It has lead bindings. It has all sorts of fancy types. But the idea is that in F star, you can annotate functions with pre and post conditions. So that means that you can say, for instance, hey, I have that super crazy optimized multiplication by 9 operation that's going to take a 32-bit integer and return a 32-bit integer, and I'm going to perform that crazy optimization that no reasonable compiler in their right mind would ever be able to figure out. I'm going to shift 3 places left and then perform an addition, and it's going to be super fast. So bear with me for the simplicity of the example. This is the low-level implementation, and you want to decorate the function with a specification that says, actually this optimized implementation is really a refinement or equivalent to that high-level, simpler specification that can be audited and trusted. And so if you try to feed that to the F-star language, the F-star language will respond, ha ha ha, no. And the reason is there's actually a bug in this implementation, which is that this is not true for any input that you might give it. It's only true if the result fits in a UN32, right? Because if it doesn't, then you have a modulo that wraps around and then you don't know what the result is. I mean, it's no longer 9 times A. So F-star is like that very pesky assistant that keeps telling you, no, it doesn't work. But the end result is that, if you're willing to take a leap of faith here, we can apply that methodology to much larger code bases and prove that a very large piece of code is meeting its specification. So the interesting bit here is that this code is blue and this code is green. And the green code is never compiled. This is all resolved statically, verified by the type checker. And by the time you're ready to compile this code, this has completely been eliminated. So the green bits are erased. The blue bits, however, are intended to be compiled. And so we have carved out a subset of F-star called low star for low-level F-star that restricts the kind of operations you can do. But the upside is if your code fits in the low star subset, it can be efficiently compiled to a C implementation. You get the blue code that compiles to C, the green code has been erased, and now you have a C function that's readily usable in any toolchain that supports C. And that's the essence of our verification pipeline. The compiler that compiles from low star to C is called KReMLin for KNRC meets ML. And it has a bunch of cosmetic things that allow generating very high quality code. So this may or may not be too much detail, so you have to stop me, but I thought it'd be interesting to take this simple example and take it to something like slightly larger. So think of it as a more in-depth version of the previous slide. Starting from the specification, which we consider to be the mathematical truth, we may want to, for instance, define a GF128, the finite field, that is actually pretty useful for a message authentication code that we use in cryptography. So this is a very small 6-line specification of GF128 in terms of a polynomial that is used to compute a field by doing a, how is it? I think it's the division by an ideal of the group, and then you get a field, and then you get the structure that you want to compute the message authentication code. I'm not a mathematician, so I have a professional review this code and tell me, sounds good. And then I can work from that as my source of truth. So in case I don't trust the person who reviewed my code, I can actually extract this specification via OCaml to a very, very, very slow and inefficient implementation. But at least I can run a few test vectors and convince myself that it's a legit specification. So after gaining confidence in the specification, I can do a step of refinement, which essentially means I'm going to write a second implementation, which I call pseudocode or implementation blueprint, that's going to be shown using the F-star proof assistant and underneath the C3 SMT solver, that is going to be shown to be a refinement of the mathematical truth. So this is a much more concrete representation of GF128. This one has loops, binary shifts, XOR operations, so you can see that it's a much more concrete representation. It's not yet something that will extract to C, but at least it's an intermediary step on the way to a low-level efficient implementation. And then my final step is to write the C-like implementation in that low star subset that will look something like this, and then do yet another proof that this refines the pseudocode, which in turn refines the mathematical specification. I invoke the KReMLin compiler to get C code out of my low star code, and then I get something like this, which is the result of extracting the verified code and generating C out of it. So this is
Jonathan,
Yeah.
you had proof in there a bunch of times. What kind of proof is that? Like computer
So
proof, mechanical proof?
yeah, so let me tell a little bit more. The proof is essentially an automated proof that the low-level implementation refines its specification.
Right.
So I would write an F-star a big lemma that says, this, this, which is like the pseudocode. I will write a lemma saying the fmul here is actually a refinement of the mul operation here. And then I will have to do a bunch of proofs on arithmetic and modulo and the representations and etc. to show that it's a refinement.
Cool.
And then I will also do a proof for this, which is that here, for instance, it's a work in progress. The only proof for this function is that it only modifies this memory location, but then elsewhere there's another proof that this is a faithful implementation of this pseudocode.
Sounds good. Thanks.
Yeah. Any other questions?
Is it ever useful to have multiple layers of pseudocode in between the specification and the low star, or is one layer in between usually practical?
We usually do one layer in between. There's nothing that prevents you from having more, but sometimes there's another extra layer if you need to unroll or switch to a SIMD representation. In that case, you will do a lot of shuffles, a lot of reorderings, and you will modify the pseudocode to a more convoluted form that like exhibits SIMD parallelism. So we will add another step.
Gotcha. Cool. Thanks.
All right, so let's talk a little bit more about compilation. So this is the nifty diagram that we have in one of the papers that describe this pipeline. And you have to trust us that we have formalized all of these steps on paper, but let's look more concretely at what's happening. And just to have, a little bit of anticipation on the next few slides, as you can easily imagine, that pipeline will be retargeted to WebAssembly. So F-star performs something called extraction, which is essentially about removing all of the proof-related things. And then the KReMLin tool takes over. There's a little bit of type checking to make sure that the code fits in that low star subset. And KReMLin has an intermediary representation that's actually entirely AST-based, because we are generating code that is C, and the C needs to be pretty unreadable for people to use it and be happy with it. So there's a lot of work that goes into doing AST-based rewritings that want to increase the quality of the generated code. Once this is done, there's a little bit of an intermediary step just to handle like scene names and scoping. And then this goes through an abstract grammar of the C language and then gets compiled by any off-the-shelf C compiler. The KReMLin compiler wants, as I said, to generate readable C code, and it wants to offer the programmer convenience and flexibility. So that's how you get this somewhat readable code. This one is taken from the Cha-Cha-20 algorithm that people would be confident about integrating. And so one of the key design choices that makes this possible is that there's never a very involved compilation step in KReMLin, in the sense that we never allow, for instance, closures in low star. If you want to go to C, you have to not have any closures in your runtime code. You're welcome to have lambdas everywhere in your proofs, lemmas, and specifications. But when it comes to the code that will be extracted, the low star subset that we saw, you don't have any closures. We could do closure conversion in C, but then it would generate unreadable code and it would be a bad design choice.
It's interesting. I would have thought that since you're targeting just a sort of small number of code bases, that I would have thought for readability, you would just have somebody take the ugly C that generates, clean it up, and then run another tool that shows that the cleanup is the same as the original.
The cleanups are not something that Clang format can do, or that existing tools can do. So there's a little bit more subtlety about that. Was that what you had in mind? Like something like
I meant somebody like manually writing the cleanup and have a tool that does the check that they're equal.
Oh, we have too much code. We have like 50 or like 60,000 lines of code. That's too much.
Oh yeah, that's why. I thought it was a smaller code base.
Yeah, I can show all of the code. I mean, these are just snippets, but like seeing the amount of code that we've like written and verified so far, it's not feasible to do manual like fix-ups. So, I mean, it's a lot of like really simple things, but that really make a huge difference in the end. So for instance, F-star will introduce a lot of intermediary variables, which are not the end of the world, but people are really upset if they see a lot of UU underscore random number underscore randomly generated name, even though it changes nothing from the point of view of the C compiler. You can use inductives in F-star, like data types, and these have to be compiled very efficiently and without any extra verbosity. So there's like 5 compilation schemes for inductives. People like polymorphism, so they have polymorphic helpers, but KReMLin will monomorphize those. Unused type and function argument elimination, tuple elimination, all of these things essentially aim to give the F-star programmer more flexibility by giving them a little bit of like leeway in terms of what they can afford to use in their runtime code, knowing that the KReMLin compiler will still generate pretty code.
Are all those transformations in the trusted compute base, or are they verified as well?
No, they are not verified. The KReMLin compiler is not verified.
Okay, thanks.
I have a plea for verifying it at the end of this talk by going to WASM, of course. All right, I'm halfway into my talk. Let's talk more concretely about WASM. So that was 2017, what I've described. And so when WASM came out a couple years later and got like the notoriety and the stability, and we realized that it was very easy to retarget this compilation pipeline to WASM. So essentially what we did is that we keep most of the existing rewriting passes, and instead of going to C, we just go to a little bit of a new intermediary language called C-flat, and to a WASM abstract grammar. That extra repurposing of the KReMLin compiler only cost 4,000 lines of OCaml code, which is not very much. So it was a good success story that it didn't take too much effort to retarget WASM. And now the question is, why bother adding a WASM backend to our in-house compiler as opposed to going to C and then using the existing C to WASM pipeline? So it's an interesting question. One of the reasons is that we eventually have hope of verifying this compilation to the chain and no longer trusting it. So we would like to have an end-to-end verified compilation that goes to WASM. And we think that it's a little bit of a stretch to verify all of LLVM, but it's not impossible to verify something that's a functional compiler that doesn't have too many fancy passes and that essentially goes to WASM directly. So one of the advantages that we see in targeting WASM directly is that it's simple. It's even simpler than when we were going to C, because a lot of things such as having to exhibit a statement-based language out of an expression-based language when going to C is no longer needed because WASM is expression-based. It was also very easy to formalize on paper. We submitted a paper at Oakland, I think 2019 or 2019 perhaps, and it only took 2 paper pages to explain our compilation scheme to WASM. And one of the other reasons why we rolled out our own backend is that we were looking at things like mscripten and going to asm.js, and we could see very aggressive optimizations that sometimes broke the side channel resistance that was baked into our code. So we were able to also verify that our custom compilation backend did not introduce side channels. There's many drawbacks, of course, to rolling out your own. The first one was that we were generating unusual code, not coming out of LLVM, so we crashed binary in. Another thing is that, and maybe that's not true anymore, I think that work was a year and a half ago, but what we found was that for good performance, you do need the kind of optimizations that LLVM performs. Like we thought that the JITs would, in the browsers, for instance, would perform a lot more work than we thought. So inlining, for instance, and I'll talk about that in the next few slides. There were also a few mismatches, so we had to add like maybe 1 or 2 extra like AST rewritings. And another drawback is that, well, we roll out our own stuff, but then we don't have like compatibility. We can't mix and match code compiled by us and code compiled by LLVM. So just a little bit of a quick word about what that took, repurposing the compiler to WebAssembly. So we were able to ditch the expression to statement phase that was needed for going to C, which was great. There were a lot of C-related subtleties that were not needed for going to WASM, so that was also great. A lot of rewritings were very cosmetic things that I talked about before because people wanted to read the C code, but we can like remove all of these, which actually increases our trust in the KReMLin compiler because we can disable a lot of its passes. A few things had to be added. So one of the biggest things, actually the sole big thing that I had to add in the compiler was that the multiple value proposal for WASM was not ready. And so a lot of the code was relying on passing structures around by value. For instance, if you have a 128-bit integer, you will pass it around as a struct in C that has 2 values. And so I had to add a pass that would rewrite all of the code to pass all of these by address and to make sure that all structures had addresses in memory all of the time, which is what happens underneath the hood with a C compiler. Like the C compiler will do all of that for you. There were a few C standard library built-ins that had to be re-implemented, like memcopy and memset. And there was one difficulty with mutable globals that we're making use of, and that generated link time errors, so that had to be hidden behind getter and setters. There's only a micro runtime system, which is just managing the call stack and allocations on the stack, which is used a lot in cryptography. And we don't support heap allocation yet because we're mostly focusing on extracting crypto algorithms for now, not the rest of the Everest stack. And the crypto algorithms don't do heap allocations, at least the ones that we consider. Yeah, and that's it. That's just like these few optimizations were added to the KReMLin compiler. Because we were on our own, another like drawback that we had was that we had to roll out our own minimal tooling on top of the code gen. So for instance, because we were doing our own backend, I designed a calling convention that would determine the layout of arguments and in memory when the function was being called from JavaScript. And so when you want to call the code generated by my compiler from JavaScript, you have to be aware of the way that my compiler generates code and how that generated code expects the arguments to be laid out in memory. Fortunately, that can be automated. So with my student, we wrote a tiny bindings generator phase that is capable of doing that mostly automatically. There's a little bit of a mini linker that will link together all of the modules generated by my compiler, handwritten in JavaScript. And then there's some shims to interface with the rest of the world, but that's like not very much so. So I think I have a demo just to convince you that it's real and that I'm not. Yes, so this is a test from curve25519 that is like compiled into the browser, and it says success. So basically it's just to show you that it exists. All right. So what did we do with that new compiler architecture? The first application was WebAssembly, that essentially aims to replace the hodgepodge of crypto bindings that are out there. So our pitch is as follows. There's a lot of crypto that you need to call from JavaScript. And there's a lot of things that you can call. There's web crypto, but web crypto doesn't have the latest algorithms. Of course, you have a node package, but then you're calling OpenSSL, which has the issues that we know. The asm.js stuff may have the side channel issues. It's slow, it's big. And you may even want to deploy your custom schemes. For instance, Signal has a modified version of X25519, and there's no way this one is going to make it to web crypto because it's too specific. So what we offer is you're a new crypto library for the web with the latest algorithms that can have all of the sensitive data isolated in the WASM memory and hidden behind a JS closure, which gives you a greater trust and greater assurance. And of course, also has a synchronous API, which is great because web crypto is asynchronous and some people might be stuck with contexts where they're not yet using promises. So we managed to compile essentially all of the SIMD-free crypto that we have. That's a big list of algorithms. I'm not going to read them all. The only thing that we had to do was that we had to implement two intrinsics that we were using pervasively through our code, add, carry, and subborrow. And we had to prove an implementation of uint128 because all of our code was assuming the existence of a uint128 type, which WASM doesn't have yet. The second application, and if you remember the pyramid, there was the crypto in that corner, and then there was like applications on top of it. The second thing that we compiled to WebAssembly was a Signal. Signal is the protocol that we have in WhatsApp, Signal Messenger, Skype's private conversations. It's a messaging protocol that is pretty sophisticated, that uses all of the like state-of-the-art features like a double ratchet, a triple handshake, and whatnot. And it gives you, like, for good reason, it gives you good guarantees such as perfect forward secrecy, or like called post-compromise recovery as well. So all of this is good. So what we did was essentially we looked at all of the steps of the protocol, and then we implemented those steps such as initiation or response in Lostar on top of HACL star, our library of crypto primitives, and then we compile it to WebAssembly, and now we have a WebAssembly implementation of Signal that uses WebHACL star. We have demonstrated 100% compatibility for our patched version of the Signal, the libsignal JavaScript library, where instead of using a hodgepodge of web crypto and asm.js, we use just like WebHACL star for that. So what was interesting in doing that work is that we found a few things that were impedance mismatches, and I suspect that this will be of interest to this crowd. So I mentioned already structs, and I know there's a multi-value proposal under wraps, but that was actually quite annoying. And one of the reasons was because WASM doesn't have a uint128 type, we had a lot of code that was passing pairs of uint64s, and the default compilation scheme would put all of these pairs in memory and would do a lot of copies in and out of memory and a lot of pointer modifications. And we somehow, perhaps naively, expected the JITs to inline all of that away and to make sure that we wouldn't take any hit from this, but it's not the way that it worked. So in the end, our struct compilation scheme turned out to be quite expensive, and to mitigate that, I added a WASM-specific inlining pass to the compiler that would inline any helper that was under like some size, and that essentially inlined all of the uint128 helpers that were doing, addition, multiplication on pairs, and that in turn removed a lot of memory excesses and gave us like a huge speed up that actually I found quite surprising. Another slightly other thing that we're waiting for eagerly is the SIMD WASM proposal. A lot of our crypto algorithms are now offered in 3 variants: the regular variant, the 128-bit variant that works on either ARM, Neon, or SSE, and the 256 variant that works on SSE2, and the crazy 512-bit variant that works on SSE4, AVX 512, and whatnot. So web crypto offers some SIMD variants, but we can't because there's no SIMD yet in WebAssembly. I mentioned the lack of intrinsics. It's not the end of the world, right? add_borrow exists in C, like any toolchain supports an intrinsic for add_borrow that compiles to a single instruction. But there's a little bit of a inefficient handwritten implementation for that when going to WASM. And the lack of 128-bit integers was also a big drawback because we can only offer the 32-bit version of our algorithms, like for a 32-bit processor that has a uint64 type, but no uint128 type. So that was like, that's also something that we'd love to see. One thing that we're still puzzled about is that we're having a very hard time like understanding where the performance hit is coming from. So we have a toolchain, we are doing some amount of optimizations, and then we don't have a precise mental model of, can we rely on a JIT to do this? Can we rely on a JIT to recover that? Should we run our code through binary in and see if it does anything? Like, I think, at least for me, speaking for myself, I don't have a good like representation in my head of what's going to happen in the JIT and what should be optimized ahead of time, and what is the like most rewarding optimization that I should implement in KReMLin if I want to improve the performance. The developer experience, of course, it was quite early, so DevTools have gotten better since I wrote the initial variant of the compiler. But as I was mentioning, like knowing where the hotspots are would be really great. And I know also that there's a proposal for Wasm Dwarf. So I'm not, not saying anything new, but like when I was writing the backend, I ended up writing a little custom debugging protocol that would allow me to break and examine the value of some things and like do some sort of tracing through the outer part of the code, like having some hooks in JS for doing some traces and just figuring out what was going on. Some things that we have our eyes set on. One of the things is CT WASM, constant time WASM. Our code initially is guaranteed to be side channel resistant for the like most obvious memory and timing side channel attacks. Essentially, we guarantee at the level of F star that you can't use secret data to either access memory or perform like direct comparisons or non-constant time operations. And it'd be great to have like a constant time discipline to just be able to show that these guarantees are preserved all the way until the end. And we hope that we can keep all of these guarantees until the end of the pipeline. I mentioned all the extensions that we have our eyes on, and we all hope that these will land soon. And another thing, and that's an open question for me, like if I wanted to mix and match code coming from my compiler with code coming from LLVM, is there an interop format or a standard ABI that would allow composing multiple WASM modules together? On the roadmap for engineering, I'm trying to wrap up so that we have time for questions. On the roadmap for engineering, essentially, I'd like to extend the backend to target the ongoing implementation of Cindy. I think it's pretty widely implemented now, at least the basics. So it'd be good to have, a prototype, if only to make sure that it works, or to submit feedback if it doesn't. If CT-WASM makes progress, I'd love to target it. There's a few improvements related to the modularity of the generated code, and essentially like performance improvements, wondering if there's like any other low-hanging fruits for performance. The more interesting bit is the research roadmap. And like one thing that I want to state here is that all of what I've said is very specific to crypto code, because that's been the heart of our work compiling to WASM. But the way that I see this is previously people were doing verified compilers all the way to machine code, and that was really bad. And WASM is so much more high level than assembly, like x86 assembly, that I feel like the low star DSL is almost a one-to-one match, modulo some like tiny tidbits, of course, but almost a one-to-one match with WASM if you take into account like multi-value, for instance. And so to me, there's like a great opportunity right there to do a very simple verified compiler that would go from the low star subset directly to WASM. And that would give you a complete end-to-end verification result at a much lower cost than doing like a full verified compiler going to machine code. For that, I need to find the right student. So if you know anyone, just send them my way. Yeah, that's it. And yes, 10 minutes. I'm sure there will be quite a few questions.
I work on Binarian and LLVM and Emscripten and all those tools. So Just to answer a few of the questions you had in
Yes.
your slide, binarian is definitely still necessary. In Emscripten, under any optimization flags, we run it on the output of LLVM, and we still get, if I remember correctly, it's like 15% code size reductions. And I don't think we measure performance, but you can expect performance improvements as well. For example, binarian will do inlining for you. It has its own heuristics for that. Also, WebAssembly specific optimizations like minimizing the number of locals, redoing the control flow to sort of make that optimal, all sorts of stuff.
Because for simplicity, I have a very generic scheme that generates a ludicrous amount of locals, but my mental model is that there would be, I don't know, like a linear registry allocator in the JIT that would take care of all of that for me. I see Russ shaking his head.
So sort of the model for WebAssembly is that as many optimizations as possible should be done on the toolchain side, leaving the JIT to do very little work. So I mean, register allocation is one of the most important things that the WebAssembly engines do perform, because obviously the tool chains can't do register allocation. But most other optimizations are expected to be done on the toolchain side. So the engines really won't be doing very much.
That's helpful. For instance, like for me, not being I've never looked at any of the JITs in the browser, so I don't know what they do. But I think experimentally, I found out, what you described, which is that they do little and expect a lot of things to be done ahead of time with the toolchain.
Yep, absolutely. And then also the multi-value proposal has shipped everywhere, including in the latest node, I think, but it's on all the browsers. And SIMD should be hitting phase 4, which is basically the phase where we start shipping it and stop changing the spec in a handful of weeks. So that's coming up very soon.
Well, that's excellent. I didn't know that multi-value had shipped before, because I thought it was still marked as a proposal or something.
It's probably still marked as a proposal, but so if you go to the proposals sort of summary page, I'll link it. There's the multi-value proposal. So this should be a phase. Actually, it's a phase 5 proposal now, so it's not even on that page. So it's fully standardized and merged into the latest.
Okay.
Yeah.
Okay.
Yeah.
So I'm out of date.
Yeah, but
Thanks.
I mean that's relatively recent on the grand scheme of things. So, and SIMD's coming, but it's only 128-bit for now. So, I don't know how much it's going to help you if you're 256 and 512-bit versions of the crypto libraries.
128-bit is pretty good already. I think it makes it's a big jump in performance.
Cool. Yeah, that'll be exciting to see.
As for the JIT, so there's multiple tiers of JITting, and the first one, just the get your stuff compiling, just says every local basically gets a stack frame or gets a portion of the stack frame, and you just block that out, and they don't do any register out. They do eager register allocations. They just go as once they hit a label. Okay, here's what those registers are, and then those get pinned there. I think the second tier is what does now the linear pass, where they actually go through and say, okay, what are these locals are actually being used? What's the lifetimes of those? And then do some more advanced register allocation. I'm not sure a lot more gets done in the second pass. Thomas, do you know?
There's also GVN and some amount of invariant code motion, but there's a lot of assumption that things are done before. It's really only the things that can't be done before because they're inherently architecture specific that get done in the backend, in the JIT backend.
Anything else on that line? It's just...
Any other questions or?
Hi, Jonathan. First of all, it's lovely to see you. How are you doing?
Surviving, you?
Doing okay. I have just like a somewhat silly question that maybe has no answer, but I've been intrigued by this difficult seeming proposal that some folks have to do flexible SIMD in WebAssembly. As like, is it possible to write code that is oblivious to the underlying hardware vector length? It sounds like the current strategy that you'll have is like pretty much hand-tuned for each of 3 SIMD widths. I was wondering, like, to you, like, how science fiction does it seem to have code that is in some sense oblivious to hardware vector lengths? Is that completely impossible? Like, maybe possible? Like, very possible? Which one do you think?
I would say very possible. So it's actually something that me and several other collaborators, especially at NREA, have worked on, which is that we don't want to be verifying code for every width.
Right.
Because there's always new widths, and also the code is always the same, and it's like a ludicrous effort. We don't have infinite manpower. It takes 2 years to train a student. So
right.
We have to be smart. And one way that we've tried to be very smart about it is essentially through metaprogramming. So one of the big recent pushes in Everest, and I can tell you about it in a lot more detail, is offloading a lot of the work at the meta stage, where you write something that's super high order, like an implementation of a repeat SIMD combinator that's going to chunk your input data for any width of your choosing and like dispatch all of these things in chunks. And then you write like a generic poly 1305 implementation that just takes any given like width for your SIMD pattern. And then F-star will do partial evaluation. So you apply all of your algorithm to your chosen width, like 128, and then all of these generic higher order combinators partially evaluate and reduce to give you fully specialized code for that width of your choosing. And only then does the code get into the low star subset, which is the one that it tries to see. It's essentially like, I don't know, template metaprogramming or things like that. There's a little bit of it in the HACL XN paper. And actually, I have something in the works about, like I have a draft that I can send you if you want, about the metaprogramming techniques that are used to make this code super generic and to make it generic for any bit width and then specialize later on.
That would be awesome. I would love to read that if you don't mind. That'd be super cool.
Yeah, absolutely. We can chat about it. I mean, we haven't chatted in a while, and we haven't had an opportunity to grab a drink. So actually, I'd love to, chat with a face I haven't seen in a while. I always get to see people on the screen. It's exhausting.
That would be great. That would be super, super cool.
I love my colleagues, but it's just, too many.
I know the feeling for sure.
Sounds like you have something also concrete that would be useful for the flexible vectors proposal I linked to in the chat.
Yep.
So that might be something worth sharing with them to like help ground some of the discussions that they're having.
Yeah, actually, I'd love to like read that and figure it out.
I was wondering, F-sharp seems like a super great tool for this job. How applicable do you think F-sharp is outside of the realm of cryptography for just generally verifying and producing verified code for just all sorts of, important software?
So you mean F-star, the verification language, not F-sharp, the existing.
Sorry.
Yeah.
F-star.
Just making sure, because there's a lot of confusion sometimes.
Yep.
So it's also a good question. I think what happened was that cryptography was a low-hanging fruit because it's easily specified. It's input-output, right? It's a functional spec, and you just need to replicate that in an optimized fashion. So that is kind of, level one of like the verification endeavor. And as we level up, I think we've been trying to look at more complex things. So for instance, like I'm working with one student on protocols, which is one level up in the sense that a protocol is more asynchronous, has a state machine, has transitions that are not necessarily, in a sequential order. And so we're looking, for instance, at the noise protocol family and asking what we can say about an application that would use all of that crypto that's been verified already and like doing peer management, state machine management, and offer an API that's decent for like clients. So to answer your question more like candidly, perhaps, I think a lot of the machinery that we designed around 2017, Lowstar and whatnot, served us well for crypto. But we essentially need to, there's an effort that's underway to overhaul all of that base infrastructure with a better foundation using separation logic, a real notion of concurrency, and that will enable a lot more use cases. And there is ongoing work in the Everest ecosystem on that, and we actually think that with like separation logic at the core of the formalization, we'll be able to have a much more expressive foundation for all of these future things like protocols, state machines, and like distributed things. It's just underway. It takes a while, but we're making progress, and I think we are moving up the stack. When you compare what we were able to do initially, like in 2017, it was simple algorithms like Cheshire-20, Polygon 305 input output. Now, what we can do is like the state machine of a noise protocol, a peer management library with linked lists and like associative maps, plus like high-level APIs such as the incremental API for a hash, where you have that little internal buffer where you store data, you only flush it when it's reached the full block, and you have a non-trivial state machine associated to that. So like we are like steadily moving up the stack and getting to more complex kinds of software.
Great, thanks.
I remembered another question on your slide, which was about C interoperability. So, in the future with sort of interface types and these other things, we hope that the WASM module themselves will be the units of interoperability, and we'll have, like a whole ecosystem built around that. But in the meantime, we do have a well-documented object file format, and this is what LLVM emits. And so, the C compiler emits the object files, and then we have a version of LLD, the LLVM linker, that links these WASM object files together. So basically, there's just this custom section with a bunch of relocation data in it. And so if you emit a module that includes this custom section and all this other stuff, then you'll be able to pass it to WASM LD and link it together with arbitrary other C, C++, Rust code.
Ahead of time.
Yep. Yeah, ahead of time.
I wrote like a very, very, very degenerate version of that where I can link together at runtime like modules that have been emitted by my compiler, where each module, points to the start of its own data segment in memory, and then all of the constants and globals are laid out sequentially in the memory. Yeah.
So Inscription has dynamic linking support for doing that at runtime, but it's not as stable as this document here, which describes the sort of static library ahead of time linked version.
I have no reason for doing it like dynamically, other than it was the simplest thing, and I also wanted to understand precisely how.
Yeah, makes sense.
I thought of a high level thing, which is, so WebAssembly right now, the sort of transfer between modules boundaries, either here's an entire memory, or here's one integer at a time kind of thing, or a few integers at a time. I feel like for crypto, you'd probably want something like in the middle. Is that? But I don't know what intuitions you have there. Like, what's useful for getting better I/O pipelining going through?
I think for crypto, it's only like integers and like byte arrays. So,
and you're finding it's fine just to be like, here's the entire memory, or would like things like views of memory is something that you could pass like first class would be helpful or not?
Yeah, it's a good question. I mean, right now it's very raw, right? You just pass like into the global memory. I mean, I think it like kind of relates to the general question of how to segregate really important safe data to different parts of the memory. That some people, in x86 use enclaves and like different like memory protected areas to make sure that their secret data is kept, really separate from the rest of the data. I think it'd be maybe interesting to have that WASM, like a notion of really like protected memory area. But right now we're achieving this with closures. We just allocate the WASM memory, like hide it behind the closure, and then only expose the safe entry points so that the rest of the application cannot modify the memory. So maybe that's enough. I don't know. As to whether views would be important, I mean, in our view, it's a very like, it's a very narrow vision, which is that by virtue of the code being verified, and if we didn't screw up the compilation toolchain, then we're not going to trample any memory, right? Like, there's no need for a view that would protect what that function can do because the function is verified. So either you're calling it with, a precondition that's violated, and then it's your problem, or, there's a compilation mistake and we're going to fix it. So I haven't thought too much about views in that context. I guess it'd be more useful, of course, if you're linking with legacy code. If it's legacy code, then yes, there will be bugs, and then yes, it would be wonderful to have a view that restricts how much the function can screw up the rest of the memory.
Wait, now it sounds like right now you're finding that the crypto components are sort of outweighing the read and write process anyways. So maybe it's not so important to optimize that because you're saying using closures and stuff that is sufficient.
Oh yeah. I would say that right now the cost. I mean, okay, let me refine that. It depends. The thing that we've done for Signal is, it really depends, right? Because if it's the asymmetric crypto, it's slow anyhow, and you don't mind copying stuff from the JavaScript memory into the WASM memory and then running your crypto. But like, we have never had like a high throughput application that we need to do a lot of symmetric crypto, and where the cost of copying data from JavaScript into WASM, run the encryption, and then copy it out would be prohibitive. So it is a good question. I think I can imagine that there will be such like a limitation in the future if there's a use case or like a setting in which you do need to do like a lot of throughput and you end up going back and forth a lot with WASM.
Right now, it sounds like it's not. You have enough applications that you're serving that without that.
So I mean, one thing that we haven't had the adoption that we're hoping for that library. I mean, I thought it was great to have a consistent library of crypto primitives that had all of the modern stuff and verification guarantees, but like, I tried to get the people at Microsoft to use Skype to use it, but I think it got deprioritized in favor of the new Teams thing. So they had a lot less interest for crypto, and I don't think Teams has, like, as of now, a big like story about end-to-end encryption. So that didn't quite work out. We were in talks with the Facebook people who were quite interested about having it for their WhatsApp web version, but then they needed something custom for the group feature because there's like a key exchange to do for groups that is not part of the base Signal protocol. It's like an extra feature to like handle groups, and we didn't have that, and we didn't have any student who was willing to implement that feature, and I had a million things on my plate, and it seemed like, it kind of fizzled out. So in a sense, like, we never got to the stage where it would be like really battle tested, and then there would be people who are really pros and can give you like performance metrics from like many machines and many different settings to see what dominates. So I think that's why like I haven't reached the stage where this would be a problem.
Makes sense. Are there any more questions from the audience, or Jonathan, do you have any more questions to ask the WASM crew?
No, the links with all the proposals and whatnot, and like all of the tidbits about what I should expect from JITs was actually super useful. So thanks, like, everyone, and Thomas, for your like detailed explanations. That was quite worth it. I'm glad I showed up.